An elegant method. Let's try. No, it's just technology is not going to work with me at all today. So I cannot annotate. An elegant method is taking a look at your delta H and your delta S, them both being negative. Sets you up with a way to figure out the answer to this question. The less elegant method would be a lot more brute force, but that's now taking into consideration how we can solve for KEQ. K equals e to the negative delta G RT over RT, sorry. Do we know all those terms? Okay, so yes and no. For those people saying no, I would agree. We don't know all those terms. We don't know delta G. But for those people saying yes, we know delta G because we have delta H and delta S. Okay, so what you can go through and do, sub in your terms, 107.6 kilojoules per mole, minus your temperature. Those delta H, delta S's, any idea what temperature those are at?
25C.
I'm going to bet they're at 25C. Technically, we don't know, right, because it wasn't clearly stated and we aren't seeing that little standard state, 0. But I'm going to bet that was the intent. Times the delta S, negative, we could say 136.7 joules per mole Kelvin. What might we do almost immediately? I would argue you should do immediately when solving for the delta G. I would actually go the other way. I'd convert the joules into kilojoules. So we can do our decimal shift. We're looking at kilojoules. So now that when we run that calculation, we can do just the straight, we'll call it subtraction for the moment, but it'll end up being addition. Okay? 2 approaches, start working on them. You've got the underlying mathematics set up on the boards. It's now just a question of plugging and chugging to get some numbers. Expression. Our value for 8.314 for R was in joules per mole Kelvin. If we're going to get our units to cancel, that's why you wanted to go to joules. Maybe that was smart. You have to ensure that you have the proper units on that. So I went through and swapped it out to kilojoules. If you had preferred to keep it in joules, you could have. You just would have had 66,000 joules.
Where did you get that temperature from?
Which?
298 Kelvin.
298, I'm making an assumption that was what was intended within this question, but I genuinely don't know. Okay. That should be more explicit with this delta H and delta S, right? To see a standard symbol in the upper right-hand corner. Right. So what we could do is find out what happens, because if the delta H and delta S are representing for this, we'll see an expression that doesn't make sense at the end of the calculation, which is mildly obnoxious, but if we don't know, we don't know.
So what is that 595?
So the 595 Kelvin is another piece of information, okay? KEQ at 595 Kelvin is 200. So what we're doing is testing it at 298 to see what happens. Does that make sense? What do we get for an answer on this? Question's been up for a little bit.
1.027.
Just 1.027? Yeah, that's fine. I was just checking. Do we get a second on that? Yes? No? Maybe? Yeah? Okay, so what's happening to KEQ as you increase the temperature? It increases. What would that mean? A KEQ that's larger than 1 would be spontaneous. Right, so as we add heat, it increases its spontaneity. Does that make sense? What happens if we evaluate delta H and delta S? Negative and negative, what does that mean? What do we see within that expression? Is this spontaneous always? No. It may start spontaneous, but it's temperature dependent. When is it not spontaneous? When our temperature gets big, a large temperature, we get non-spontaneous. So we're seeing the opposite relationship here, so it's puzzling what's going on with these numbers. And it's possible that there was a math mistake done through there. Okay, so that delta H, delta S, and KEQ may all be for 200 degrees. I'm not sure what's going on with those numbers.
Well, I got a bit of a different number. I got 5.25 times 10 to the 11
For what?
for the K. It's a little bit different.
Yeah, and not only just a little bit different, that's on the opposite spectrum for our magnitude,
Yeah.
right? So that would be at a low temperature, we're seeing it be
Very
more spontaneous, which would come into line with this. Okay, but we now have two different values for K. Who's right?
The second
Okay, that's going to come down to those individual checks, and you would have to check your mathematics behind that and make sure. Okay, we're getting confirmation of the second one, which means you did a math error in your calculation.
So, is the reason is R normally in terms of joules? And that's,
Yes.
Okay.
Yeah.
So you have to convert it to kilojoules?
Yes. R is usually given in terms of joules because we don't want to memorize fractional, small decimals like that. So we shift it up to joules so we can get 8.31 as opposed to 0.00831. It's just a preference in how we would memorize that number. Right? So what happens at low or at higher temperatures, our KEQ got significantly smaller, right? Which matches our system over here. At higher temperatures, we start to shift towards non-spontaneity. Are we there yet at 595? No. Okay, but what we're looking at is the trend in that system. Yes, sir. Where did I get that this was higher temperature?
Yeah.
Okay. So this discussion right here has only to do with the sign on the delta H and delta S. Okay? All of this mathematics is a whole bunch of work. That, I would argue, is a brute force because this question just says, how does it change as your temperature increases? Okay? Well, since we know KEQ is related to delta G, if we understand what's happening with delta G, we can predict what's going on with KEQ. I don't need numerics because the question doesn't ask for numbers. Right? I can use them if I so choose. That goes back to our enthalpy and our entropies. Right? The one part that actually works here, no, that wasn't it. That would be, oh my goodness, it's way the heck back there. Remember that table? That would, the elegant solution to this is just looking at that table. Right, and figuring out where that places everything. Right? So it's spontaneous, but only at low temperatures, because at high temperatures we switch to non-spontaneity. Delta S is negative, delta H is negative. Does that make sense? Okay. All the calculations we've written out are just a way to quantify that difference. Does that make sense?
Use the table. I'm trying to understand why these signs are the way they are and what that means for spontaneity.
Cool. So first thing, spontaneity. When do we have a spontaneous reaction for a delta G? It has to be a negative sign, right? 50-50 question, right? So if you're getting that wrong, at any percentage, that needs to be noted somewhere in your notes. That a spontaneous reaction needs to be a negative delta G, right? After that, you're now evaluating what's going on with your delta H and your delta S. Okay? Delta H is your bond enthalpies. That can be quantified, or is usually quantified, but we could also go through and state it as exo versus endothermic. Right? That's going to give us that sign information as well. For our entropies, again, we can quantify it. We can look at the sign of that quantity. We can also evaluate how did it change across the course of the reaction. That goes all the way back to even earlier in this, well, sort of here, because it asks about entropy within this slide. So the number of molecules, the phase changes, those kind of things. Does that make sense? Once we have those signs, now all we're doing is subbing the signs into our expression for delta G. Our expression for delta G is delta G equals delta H minus T delta S. So all I'm doing is dropping in the signs for those possible things and say, what does that mean? So if I simplify the expression as written right here, I get negative plus temperature. So when am I going to have a spontaneous reaction? When this value, my temperature, is small. When am I going to get a positive value? When this temperature is large. Does that make sense? If you don't like saying slide, sorry. Where are we? 48, you still got. Whoop. How are we feeling on that? Okay. So how does increasing the temperature affect the rate of the reaction? Another blue box, and if we look at it, there's nothing on these slides. Okay, so this is now just a question for you to kind of ponder and potentially start drawing diagrams that might help you describe what's going on. All right, we'll give you 30 seconds to talk at your table to figure something out. So technology is not recording nicely, so instead the only way I can get it to record, and it's not going to show any writing on the screen either. Never mind, that didn't fix anything. So you're just not going to get any writing for this one. How does increasing the temperature affect the rate of the reaction? What do you guys have?
It increases the rate of the reaction.
Why does it increase the rate of the reaction? What happens when you increase the temperature?
There's more energy in the system, and because there's more energy in the system, there's more movement in the individual particles, more likely for collisions to happen, and that therefore increases the rate of the reaction.
Cool, I like that, but I would actually argue those are two separate concepts. So more energy in the system, which means more particles collide. More collisions does potentially lead to more product, but just because you have more collisions doesn't mean you get a product, right? What else do we need? Orientation. Temperature's not changing that. What else does the temperature affect? The force of that collision. So what you're referencing is the activation energy. When you heat it up, you're sliding that curve so more particles clear the activation energy. So it's more collisions, and in those more collisions, more particles have enough energy to make that process. So it's really two kind of separate but related concepts.
Could you also just use the Arrhenius equation as you just did?
So you could also go through, instead of thinking about it in a kind of qualitative sense, you could start to go through and plug numbers in and see how that would affect the rates of your reaction. Okay, so two more questions. How does the increasing, never mind, one more question. Which rate constant increases more when temperature is increased?
It's asking which rate constant I was wondering what different rate constants are.
Cool. Okay, that's a good nuance on this question. Okay, what rate constants are we talking about? We're looking at equilibrium. We're looking at the forward reaction and the reverse reaction. So when we're talking about the rate constants here, what rate constants are we comparing? The rate constant for the forward reaction and the rate constant for the backwards reaction. Okay? what was also said was you're looking at the reactants and products. It's not about reactants and products, it's about the directionality of your reaction. Okay? So again, which rate constant increases more when you increase the temperature? Start the recording. Oops, didn't mean to start the recording. What does that mean? What's going to happen to our K? Because when we increase that temperature, and I would argue it's based off our energy diagram, okay, if we increase our temperature, what's going to happen? More reactants clear that activation barrier, okay, and we can progress forwards. Okay, what does that mean about the reverse reaction? So our K is going to get larger and larger. If the K is getting larger, Kf can get bigger. What does Kb need to be doing? It needs to be getting smaller, the same or smaller, right? To maintain that K getting bigger. Yeah. Your activation energy isn't changing. I'm going to sit and stew on this one, unfortunately.
I mean, you can see it equation-wise, like same thing that already used.
There's a little bit more information in the slides that is contradicting that statement. That's why I need to stew on it. As we increase the temperature, our particles increase in population. Okay, it starts sliding forward. It squishes that curve a little bit. As it squishes it, we get a little bit more particles clearing that activation barrier for that forward reaction. That's what's now pushing us and getting more products across, which is exactly what you were stating earlier about what's happening with your increase in temperature. Right? So how do delta G and KEQ change as the temperature increases? We've got more delta H and more delta S's that we can look at, and we can start to think about how those things are going to change and manipulate in those individual systems. Do we have temperatures to plug in? No, but do we have potential to do other options for this? You just want your temperature to increase to see a numerical change. Okay? So what you can start with is an assumption that your delta H and delta S don't change much. Okay? And start subbing in different temperatures and see what happens to those end results. So give it a shot. This is what's happening. Those rates are going to go through and change, but because we're changing the relative delta G's, we're also changing significantly the KF and KB, or K forward and K reverse. Okay? This is what's affecting our equilibrium constant, and that's going to manifest in our overall energy diagram and reactions. Does that make sense? So what we're doing is we have to be aware of those changes as we navigate it. Okay? That can be very tricky to understand and manipulate. So what can we do as a crutch to navigate that without having to think as hard about it? Exactly what we just walked through and did, math. Sub some numbers into the system and figure out how it changes. Does that require time? Yes. Because it requires time, that might be something you leave to the end of a quiz to go through and navigate. Kind of, sort of? Yeah.
So when I was testing temperature, I tried to do 320 Kelvin, and that wasn't enough because I still got a positive delta.
That's why I think it happens.
Wait. I would argue it is absolutely enough. Sorry, temperature, you said 320?
Yep,
What'd you get for delta G?
165.08 kilojoules.
What did you get for your K?
1.16 times 10 to the negative 3.
It is absolutely enough. But I didn't see the delta G switch from negative to positive. You don't have to. What's happening to your delta G? If we go here, it's going positive to negative. To go positive to negative, what did the value do? It decreased. What happened to your value? It still decreased. The magnitude of that decrease isn't as drastic if you don't pick a, in this case, wickedly toasty temperature. But you can still see the change. So it doesn't matter what number you put in as long as you can see the change. Okay? Which does get dodgy, because if you picked 300, it's going to change, but how much is it going to change by? Not a lot. So within rounding error, it might look like nothing has happened. Okay? So 320 didn't change a lot, but it changed enough to see the magnitude. Does that make sense? So we're not necessarily seeing a full change, because remember, we're going from reactants being lower in energy than the products on our energy diagram versus reactants being higher than products. So what's happening as I heat it up is this slowly starts to creep, okay, until they switch to the final thing. That creeping is what you're calculating. The rate at which it creeps is going to be that temperature dependence. What's going to determine the temperature dependence? Is delta H going to determine the temperature dependence? It's delta S that's going to determine the temperature dependence. If the delta S is very, very, very large, to a certain extent the delta H, it's the relative positions of those. But a larger delta S is now going to be multiplied by that temperature. You're going to see a stronger temperature dependence in the overall reaction. Okay? And that's, again, going back to delta G equals delta H minus T delta S. And so what you're playing with is those numbers to see how those magnitudes change. Kind of, sort of? Okay. So, how does increasing the temperature affect the equilibrium constant? Right? We could go back through, we could evaluate all of these systems. This table should look really familiar, right? What does this table look like? The thing that you asked about, and I frantically scrolled backwards in the slides, and I should have just gone forward like 4 slides. Right? And this is that table that relates delta H to delta S, and ultimately what that means towards our delta G. So that spontaneous, the inside of that boxes is all the delta G's. Right? So this table gives us lots of useful information about delta G, but it's not telling anything to us about K. So what could we start to go through and do? Let's add some K values. So depending on those, which box we're in, right, we're talking increasing temperature. So your K is going to be larger than 1. What's going to happen to K through the course of the reaction or changing that temperature? Right? It's going to decrease. Why would it decrease? What's our energy diagram looking like? Right? For that upper quadrant, what am I writing? Negative delta H, positive delta S. What's our delta G? As a hint, spontaneous is our delta G. I wish I could draw on this so we could color code those things separate from each other. Spontaneous is our delta G, which means our delta G is negative. What does that mean our energy diagram looks like? Reactant, product. Okay? What happens as we increase the temperature? These are going to start to level out. We're going to increase the speed of our product reaction. And what's going to happen to our K? It's going to decrease. Why does it decrease? Because as I add temperature, what's happening? I get progressively more and more products. Okay? And that's going to set me up with a K decreasing. Oops, sorry. As we increase that temperature because the system we have to deal with our delta S. It's not increasing it, it's actually shifting the other way. It's becoming increasingly more spontaneous. Okay? So the deciding what happens with your magnitude of temperature changes is heavily dependent on which quadrant you're in. So you have to pay attention to that quadrant within the context of that question. Okay? My recommendation, I would split this quadrant. For me personally, I would color code. Above the line, I would reference as my delta G. Below that line is my K. Right? Above that line, spontaneous, delta G. I'm now looking at Ks. Note what's happening. Right? Depending on the temperature, I'm getting a different magnitude in K. Kind of see the systems? This is also going to extrapolate out to the other systems. Right? And what's having that effect is that relationship between the magnitude of your delta H and the magnitude of your delta S. Right? Your temperature is now a way to effectively alter or manipulate how delta S, how important the delta S becomes to the overall reaction. Kind of, sort of? See, a lot of people copying this slide. You have the slides, right? There is no need to copy a slide as long as you know to look for the slide deck. And if you're like, where's the slide deck? It is in Canvas, and we'll push on this even better because you know there's no page numbers on it. This is slide 69. Right? So you can immediately flip to slide 69 and you now have this very powerful slide. Okay?
It's a very succinct slide.
Say again?
A very succinct slide added to.
Can you
Yep.
go back for just a
Whoops,
second?
yeah.
Because ours isn't that detailed. Ours just shows spontaneous or not.
What yours, scroll a little bit. Let's see if it does it this way. So because of how you're opening it, depending on how you're opening it, you may see it as slide 70 maybe, or even significantly later than that, because there have been some slides that have animations flying in. This is an animation slide. All right, so if you're opening it in PowerPoint, it should be slide 69. If you're opening it in something else, it might change your numbers around. Yes?
If you open it just straight up in Canvas, it's still slide 69.
Oh,
So
okay.
straight up in Canvas, it's the same number.
Is it showing this information? Do you see a slide that shows just that?
It doesn't do
All right, so what it's showing is the superposition, whichever one was higher priority. We get another summary with our temperature and our equilibrium. We've got energy diagrams, again, what I was trying to show up on the screen. Right? If we're starting with an exothermic reaction, we've got a reactant going to our product, again, flowing downhill. Okay? K decreases as temperature increases, delta G increases, becomes more positive. Right? Why does it start to increase? You're starting to change the energy of the products. As those product energies start to slide upwards, that has the potential for changing the directionality of your reaction. Okay? As we increase that temperature, the reaction becomes more reactant favored. In an endothermic reaction, as we increase the temperature, right, we're affecting to a larger extent the lower energy species. That's what's happening in each of these stages. Stages? I don't know. Let's say stages. Okay? As I increase the temperature, I'm going to see a larger effect on the reactant side. So that's going to start to slide upwards. Okay? And my delta G is going to start to become more negative. That was looking at our numbers up here. Remember? When we looked at our examples, 1,000 Kelvin versus 320 Kelvin. We saw a full switch when we went to 1,000 Kelvin, but we could still see the trend happening when we were looking at a smaller temperature change. Kind of, sort of. So again, a huge, powerful summary slide. Okay? So we've got another one to kind of crank through and evaluate. Predict what would happen to the equilibrium constant if the temperature was decreased. And explain both from a kinetic and thermodynamic perspective. How does this change in concentration of HCN at equilibrium? Okay, so a couple things that we might want to tag. I can't fucking draw. I would tag that HCN. I want to make sure I know where it is in the reaction. Where is HCN in my reaction? It's on the product side. Okay, so I would want to tie that. That's a hard part of my, or not hard part, that's a key factor in this question is knowing where that HCN is. So we're talking about how my product concentration is going to change. Right? I want to decrease the temperature. Why is this now more challenging than what we just talked about? What are we talking about? Our temperatures over here. They're all increasing. So we gave you, this is what happens when the temperature increases, but now we're going to flip it and say what happens when the temperature decreases. So now we're going to get a slight shift in that focus, and again, we want to think through that process. Kind of, sort of. We're looking at both kinetic and thermodynamic. Okay? What describes both our kinetic and thermodynamic perspectives? What thing incorporates both kinetics and thermodynamics in it? The energy diagram. The energy diagram that we started literally day one of this class talking about. Okay? That diagram is going to help you to control what's going on both from the kinetic and thermodynamic aspect behind this. Kind of, sort of. Right? You're given delta H and delta S. You also have a KEQ. Right? So again, you have multiple approaches. You can go through and start to evaluate what does your energy diagram look like, what's going to happen as you change the temperatures. Okay? Or you can go through and brute force mathematics all the way through it. Sometimes brute force it works, so you just do it. That's fine. Okay? But you have both a pictorial potential representation and I'm just going to slam numbers into a calculator to see what happens to my numbers. Kind of, sort of? Yeah. Did you have a question? Oh, sorry. I thought I saw a hand over here. Hi. I'm going to pause. Okay. If that was an S, yes, I keep trying to bring out the pen. Can't do that. What happens to the KEQ if the temperature was decreased? Say again? It increased. Right? How could we go through and know that? Right? One potential option is you've got this stuff memorized, right? And you're now flipping the signs. Make sense? Right? Tell you right now, I don't have any of that memorized. Right? But I do know how to manipulate my delta H and delta S through a delta G expression. So I plug in the signs. I'm looking at a negative value plus temperature. Right? At low temperatures, I'm going to have a negative sign on my delta G. At high temperatures, I'm going to have a positive sign. So far, so good? What does that mean for me? I can now draw an energy diagram. I'll draw low temperatures. Low temperatures, I had a negative, which means my product must be smaller than my reactant. Yeah? Or lower energy, sorry. Right? At high temperatures, it flips. Okay? In particular, I'm caring about what happens to the KEQ. Okay? Well, if my products are lower in energy, that means I have a larger product amount to my reactant amount, which means my KEQ is going to be big. What happens if I now flip it? I now have a larger reactant to product. My KEQ is going to be small. So when I'm now looking at that temperature decrease, I'm going from a high temperature to a low temperature. So what happens is I go from a small number to a big number. Well, the number just gets bigger. No mathematics. Right? How do we explain this from both a kinetic and thermodynamics point of view? Where's the kinetics? our activation energy. What's happening to the activation energy? So again, might be useful to include, that's supposed to be an arrow. Good enough? Okay, good enough. We're going this direction. Okay? So what's happening to my activation energies through the course of this reaction as I'm going from here to here? Okay? As I decrease the temperature, what's changing? Well, the activation energy for my forward reaction starts to decrease, and my activation energy for the reverse reaction starts to increase. You laughing at my arrow? Don't laugh at my arrow. Go for it.
So, I might be misunderstanding.
Nope.
At the high temp, it's like endothermic, right? So it can have a negative delta H if it's endothermic, if the temperature is high enough.
So there's an interesting question. I like that question. When is it a negative delta H?
Always, if it's good.
Right. And this is where things get a little bit shaky and a little bit weird. Is this delta H in here? No, what is this?
It's an endothermic reaction.
If we're referencing endothermic, that usually falls back to delta H. What is this? It's the what? Delta G, not the delta H. So you got to be a little bit careful in looking at that system, because the delta G is dependent on delta H, but it's also dependent on the temperature in delta S. So that's now making the diagram look like it's switching around because you're looking at a different part.
Right, but doesn't negative delta G mean it's spontaneous, which
Yes.
means it has to be not like that?
Is this a negative delta G? At high temperature, what was my delta G? It was positive.
Okay, that makes sense.
Right? What's our thermodynamic explanation? So activation energy is referring strictly to what's going on with our kinetic is what's happening with our energy, activation energies. What's happening with our thermodynamics? It's looking at our delta G. It's looking at how the temperature dependence is changing the magnitude of our delta G. That's now strictly back to the temperature affecting delta G, not the activation energy. Right? You're looking at a different part of the diagram. We're concerned about that space, which you're used to being called delta H. But now what we're looking at is that space being called a delta G. What thing is controlling that? Temperature. Temperature is changing the magnitude by which our delta S and delta H interact. Kind of, sort of? How does this change the concentration of HCN at equilibrium? All right. Well, what was HCN? It was a product. Right? If I'm going this direction, if I have a small K, what does that mean about my product concentration at high temperature? This is small products, which is therefore small HCN. As I decrease the temperature, what's happening? My K becomes big, and if I have a big K, what does that mean? More products. Big products? More products. There we go. You said more products, didn't you? Yeah. More products, which is our HCN. So we would expect an increase in the HCN concentration. Right, as we decrease the temperature. You see it all? Yes, sir.
So would activation energy increase?
Well, that is what we're seeing here, is it's manifesting that that's how it has to happen. Right? So why is the activation energy decreasing? Right? That has to do back to the balance of delta G dealing with our activation energies. G's. Those delta G's are related back to our activation energies because the difference in our activation energies is our delta G. So as the delta G changes, that's also going to tweak those two activation energies relative to each other. Kind of, sort of. We went through like 3 slides in an hour. This is ridiculous. Okay, so we could go through and calculate KEQ at a temperature of 275, okay, to confirm the prediction. This was the brute force method. Okay, we could look at what the KEQ manifested at that 298. Right? And we could just go through and say, well, what happens to our delta G? What happens to our K? Right? And then we just pick a lower temperature. Picking that lower temperature, we can plug in the numbers and we can say what happened to the size of it. Again, it's size, not necessarily switching positive to negative, but we're just looking at that, or really big to really small. We're just looking at what happened to the number. Is it getting bigger or is it getting smaller? We don't have to do a switch. Kind of, sort of? What drives almost all of this conversation? Said differently, what's written on the board? Okay? An understanding of what's happening with delta G, which was dealing with these charts and these quadrants. Do I understand how those things manifest? Right? Not only then, that gets me these signs that I can deal with, but now I have to interpret those signs. And now once I know the signs and sort of a numerical value, what can I do? What did I shift to? Visual representations looking at the energy diagrams. Right? So you have to kind of bounce back and forth between those systems to understand what's happening to the energetics. Right? You can just as equally go through and define what was the delta G at low temperature. What was the delta G at high temperature? You can quantify that. You can quantify the KEQs. Once you know those delta Gs, you can quantify all of that through running a calculation. But none of that is strictly necessary to understanding what's happening within the reactions. Does that make sense? How does increasing the temperature affect the equilibrium constant? Okay, so we've got a couple reactions here. Go through, look at these systems, and evaluate how your KEQ changes. Again, I'd really like a pen to draw with. What happened in this first system? What happened to your KEQ? All right, I went from a negative 30 to a negative 9, which means it increased. So KEQ increases when we increase temperature. Is that true? Okay, KEQ increases. What happened to your KEQ over here? It decreased. But I thought it increased. Didn't you just tell me it increased?
Different reaction.
Right? There's context behind what allows it to be an increase or a decrease. So you can't just say KEQ increases as we increase temperature. You can't just say KEQ decreases as you increase temperature. You have to recognize the context of that system. Where do you see that context? Say again, that's a valid one. I'm trying to draw a freaking thing in. Okay? We could look at the numbers. Sorry, and I was irritated with my device. The numbers that were reported here in the table, is that what you're talking about?
I was talking about the ones on top.
Cool. We could look at the table data to see what's happening with our KEQs on deciding whether they increased or decreased. What else could we try to look towards? The delta H and the delta S, because the delta H and the delta S give us information about which quadrant we're in, Once we know which quadrant we're in, we know what's going on with those changes in temperatures with respect to Ks, and we can now control or predict what's happening. Make sense? Okay. So again, what do we keep falling back towards? Probably one of the most frequent words that I've said so far in this lecture has been, which quadrant? Quadrant. These tables are going to be really, really important because they can help you summarize and manipulate through those systems. We do have to be careful, right? And this becomes one of the challenges within this. Is you go, okay, this table is really important, so I'm going to include this on as a cheat sheet. Yeah, that's good, but you have to be able to use it, right? So it's not just here it is, but it's now, do I know how to manipulate and use this table to benefit me in answering questions? How do you figure out how to use it? I didn't think that was a hard question. I said it out loud, right? Practice. This is the point of ALEKS. So when you're going through and doing those ALEKS questions that are more than likely going to be crunching numbers like crazy at you, take a step back and breathe after all that number crunching and figure out how it applies back into the table. Make sense? Okay. Cool, right? Equilibrium, constant expression. Yay, we got a simple question. That's a fun one. Okay. If we have 2 molar NO2 and 0.5 molar N2O4, is the reaction at equilibrium? Right, so we want an equilibrium expression written out, and we want to address whether it's at equilibrium. And then, you already know the answer to that question because this question shows up. Okay, what will happen to the reaction to get to equilibrium? How are the concentrations of NO2 and N2O4 going to change? Start putting some work together. Can I erase the board? Fine. Start putting some work together to see what you can get through for this. How do we set it up? Deciding if the reaction is at equilibrium, we'd have to go through and we try and calculate our K value. We're already given the K value. We're already given the K value. Why am I trying to calculate what K is? It might not align. Right? So what I'm going through and doing is writing my K expression, right? And then we get an interesting follow-on. I'll put it in red here with my equals. My red equals. Is that actually an equals? No, it's not. Because this is K. K is 217.4. That's what it is. When I go through and sub in all these numbers, I get 1 over 8. And I can't do math. What's 1 over 8? 0.125. Is 0.125 the same as 217?
Close.
No, they aren't close at all, which means this red equals is not actually an equality. Okay? So what we're doing is we're making an assumption. We're guessing, hey, is it at equilibrium? Let's go ahead and just throw it out and just see what happens. Right? And decide how that changes. Let's see what goes through. Right? So it's not technically an equality, which is why we tend to introduce a new term. Right? Instead of talking about it as a K, we'll bring in a term of Q. Okay? What is Q? It's solved the exact same way a K is. Okay? But it's not at equilibrium. If we were to look at our reaction coordinates, right, we had our concentrations and time. Our reactant goes down, our product goes up. Okay? When we're looking at that diagram, this is where we're at K. All of this is Q. Okay? And that's looking at a reaction where we started with no reactants. Why is this system a little bit different? Sorry, we started with no products. Why is this system a little different? We're starting with products. So this isn't just a normal reaction now. We're putting a random mixture together of reactants and products and saying, hey, what are you going to do? Right? And testing that to see how that changes. Right? So what we figure out first and foremost is that we're not at equilibrium. What does that mean is going to happen? Chemistry is going to happen. Okay? That chemistry is either going to be the forward reaction or the reverse reaction. Which one? How would I know? What was K? Cool. Products over reactants. Okay. And what is Q? Same deal. Products over reactants. If I'm looking at this 0.125, what does that mean the amount of products versus reactants is? There it is. Take a guess. Throw it out and say, oh, higher products. Oh, wait. No, don't do that, because if it was a higher product, the number would be bigger than 1. Okay, so what you're saying in this particular scenario is that we've got tiny little products and we have a lot of reactants because we're less than 1. What does a K value at 217.4 mean? I've got a lot of products, and I did it right. Tiny little reactants, right? Okay. Where are we currently? We are currently at 0.125 with tiny little products, lots of reactants. What needs to happen to get to K? Say again? I mean, yeah, you're throwing in a whole bunch of letters and words into that. I would argue, what do you need to do? Increase products. At the same time you increase products, what has to happen to the reactants? Those are going to have to decrease because reactants and products are tied to the chemical equation. Make sense? So if we put this mixture together, what's going to happen? The forward reaction is going to happen to a faster rate than the reverse. And we're going to start forming more products through the course of this reaction. So what has to happen for the reaction to get to equilibrium? I need to increase the concentration of products. The forward reaction must progress. What's going to happen to the concentrations of NO2 and N2O4? Okay. Well, to increase the concentration of products, what's going to have to happen to my concentration? N2O4 needs to go up. What would have to happen to my NO2? It would have to go down. Okay, because again, we're assuming a closed system within this question. Okay. With that, I've talked too much. A little bit. We've got a fun little picture on reaction extent, which is what we just talked through. There's our Q coming into the system. Okay. If you got questions, you can raise your hand. Hopefully I'll get technology figured out so that the recording on Tuesday? Oh, it's real early. So Wednesday and Thursday. Hopefully both those recordings will actually have text in them or annotation across the surface.